Imagine opening your eyes one morning and feeling, in some impossible, instinctive way, that the universe has developed a new presence. Not a sound, not a flash of light, not even one of those eerie, low rumbles you blame on your upstairs neighbor doing improvised midnight aerobics. No. This would be the quiet, uncanny sensation that the entire fabric of reality has a visitor. The way you somehow know when someone is standing just a little too close behind you in an elevator. Except instead of a stranger with questionable spatial etiquette, it is another universe, a whole self-contained reality, drifting near ours like a cosmic neighbor who never learned that fences exist for a reason. If universes had lawns, this one would already have its bubble of space-time halfway across ours, revving its dimensional lawnmower with the enthusiasm of someone who clearly lost a bet. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. Of course, you would not actually feel any of this. Our senses evolved to detect useful things like approaching predators, not approaching universes. If humans could detect cosmic scale phenomena, we would all spend our days walking around clutching our heads, overwhelmed by the ceaseless background hum of the cosmos. But in this imaginative scenario, it is fun to pretend that one morning you might peel yourself out of bed, grope for your slippers, and notice that reality feels crowded, as if existence itself is holding its breath, waiting to see if its enormous new neighbor plans to stay on its side of the cosmic property line or borrow a cup of sugar and accidentally collapse space-time. And that is the thing about universes. We have no guidebook that says what they should or should not do. We barely understand what ours is up to most of the time. It expands, it cools, it occasionally tosses around galaxies like a bored cat flicking ornaments off a shelf. It is enormous, complicated, mysterious, and very bad at sending progress updates. So imagining that there might be others out there, other whole realities with their own rules, their own physics, their own cosmic personalities, is already wild enough. But imagining those universes getting close to ours, that is like realizing the ocean you have been sailing on might suddenly meet another ocean, one where the water flows sideways and the fish whisper in algebra. As these two universes drift toward one another in this narrative thought experiment, it is tempting to picture them as literal bubbles in a dark cosmic sea, slowly expanding until their edges touch. Some people imagine this as a soft, elegant moment, two shimmering boundaries kissing like soap bubbles. But let us be honest, soap bubbles are fragile and polite, the introverts of the fluids world. Universes, on the other hand, feel more like colossal, unpredictable entities, powered by endless energy and physics that would make even the bravest scientist mutter, "I am going to need more coffee." If two such giants drift close enough to meet, The moment probably would not resemble a delicate kiss so much as two bulldozers accidentally backing into each other while arguing over whose turn it was to check the multiverse map. Yet that is precisely why this hook matters, because it jolts us into confronting scale. The human brain is a magnificent problem-solving machine, but it did not evolve to make sense of realities within realities, let alone encounters between those realities. Still, stories help us stretch the edges of our imagination. By picturing something as absurd and colossal as two universes colliding, we trick our minds into expanding beyond the familiar. We momentarily step out of our daily concerns. Did I send that email? Did I leave the stove on? Was the universe always this crowded? And instead look outward into possibilities so vast they feel almost comedic in their audacity. And humor is important here. Without humor, the idea of universe-on-universe contact could feel heavy, even ominous. But with humor, the whole thing becomes surreal in the best way, like imagining two galaxies having a polite disagreement about parking spaces. Humor keeps us grounded, reminding us that it is okay not to have all the answers, that it is okay for the universe to be weird. After all, the universe has always been weird. We just like pretending it is normal because it makes daily life easier. So the opening of this script is an invitation. Step into a story where reality itself becomes a character. A story where the cosmos has a personality, where universes can drift too close, where boundaries get fuzzy, and where even existence occasionally has to deal with unwanted neighbors. It is a playful, imaginative doorway into a much deeper exploration of what universe collisions could mean, scientifically, conceptually, and philosophically. If the idea feels enormous, that is because it is. But if it also makes you smile a little, that means you are exactly where you are meant to be. Now that the hook has cracked open the door to this cosmic scenario, the next chapters will step through it, each venturing into new territory that builds the larger picture piece by piece, without ever circling back to repeat what has already been said. But for now, enjoy this moment of curiosity, this quiet pause at the edge of imagination, where two universes drift closer, and you, a tiny but wonderfully curious observer, get to wonder what happens next. When physicists use the word universe, they do not always mean the same thing the rest of us do. Most people hear the word and picture everything that exists, all the stars, all the galaxies, all the space between the galaxies, every stray particle, every forgotten asteroid, every embarrassing comet that tripped over its own orbit. The universe feels like the ultimate container, the cosmic box that holds all the cosmic toys. But physicists, being the enthusiastic boundary pushers that they are, sometimes use the word differently. To them, a universe can mean a single region of space-time with its own internal rules, a kind of cosmic zone where the lights are wired a certain way and the physics behave according to a particular operating system. In that sense, our universe might not be the entire set of all that exists. It might just be our neighborhood. A very large neighborhood, yes, but still only one neighborhood in a much stranger, much larger cosmic city. To make sense of that, imagine space not as a smooth, endless stretch, but as a vast collection of expanding bubbles, each bubble representing a domain where space-time took on a specific shape, texture, and rulebook. One bubble might have a certain amount of energy stitched into its walls, shaping the galaxies inside it. Another bubble might have different constants, different forces, maybe even entirely different structures. And the fascinating thing is that these bubbles are not floating in any kind of conventional air or liquid. They are not drifting through a void like balloons at an interdimensional birthday party. Instead, they arise out of deeper fields and processes we barely understand, fields that make space-time possible in the first place. Now our bubble, the one we live in, is gigantic from our point of view. We measure the visible region of our universe in light that has traveled for billions of years, which is about as close as humans get to saying very, very big, without giving up and lying down on the floor. But from a more speculative cosmic vantage point, our bubble may be just one among countless others. This is where things start to feel slightly surreal, like realizing the house you grew up in might actually be one apartment in a building so enormous it casts a shadow across realities you have never even heard of. Physicists sometimes compare universes to distinct space-time domains separated by energy barriers that keep their rules from leaking into each other. Inside our domain, light behaves one way. Matter organizes itself according to familiar patterns. Gravity bends space-time with a particular strength, but those properties are not guaranteed to match whatever exists inside another bubble. The cosmos might be running different experiments simultaneously, like a scientist who refuses to stick to one recipe and instead tries dozens of cosmic flavors at once just to see what sorts of realities crystallize. Each bubble would then be one of those flavors, sealed off by a boundary that prevents everything from mixing together into one unmanageable cosmic smoothie. This is where the idea of personal space comes in, a surprisingly relatable trait for something as incomprehensibly large as a universe. If universes could talk, ours might say something like, "I am perfectly fine over here, thank you, and I would appreciate it if other universes did not poke my space-time." And for the most part, they do not. Each bubble expands on its own, stretching out like dough rising in a cosmic oven, minding its own business. There is a certain polite detachment to it, as if the multiverse has developed an unspoken agreement that crowding is rude and boundaries should be respected. But physicists being physicists, they could not help noticing that boundaries, no matter how elegant they look in equations, may not be permanent. If universes are expanding bubbles, then it is possible, just possible, that some bubbles could drift close enough for their edges to brush, creating a moment where one domain meets another. That idea is not the focus here, but it is the quiet implication humming underneath these definitions. Universes might not be isolated islands after all, but participants in a larger structure where proximity, however rare, is possible. For now, the important thing is understanding what a universe actually is in the scientific sense. It is not just space and matter. It is a self-contained space-time stage, complete with its own script, set design, and backstage physics crew. Everything we observe, from the smallest particle to the most distant cluster of galaxies, follows the same choreography, and that choreography is what defines our domain. If another universe exists, it would be performing its own dance, following steps we cannot even imagine. The funny thing about trying to define something as enormous as a universe is that the definition always feels too small. Calling it a spacetime domain sounds tidy, but leaves out the emotional strangeness of living inside one. Calling it a bubble makes it sound delicate, which is misleading for something capable of producing black holes and galaxies. Calling it everything we know is accurate, but incomplete. The truth is that a universe is a place where reality decided to take on a particular shape, and we, by extraordinary cosmic luck, ended up in one that allows stars, planets, biology, and eventually you, sitting here, listening to a story about universes that might have social boundaries. In this chapter, we are simply establishing the meaning of the word so the rest of the journey makes sense. Once we know what a universe is, a space-time domain with its own laws, we can wonder what happens when two such domains come dangerously close. But that exploration belongs to later chapters. For now, it is enough to appreciate that our universe is not just big. It might be one bubble among many, floating within something even grander, each bubble drifting carefully, politely, and perhaps nervously through the vastness of a reality far larger than the word universe was ever meant to contain. Long before galaxies spun themselves into elegant spirals, and long before stars carved themselves out of collapsing clouds of gas, the universe went through a moment so dramatic and so ridiculously fast that trying to picture it is like trying to imagine a balloon inflating from the size of a grain of sand to the size of a galaxy in less time than it takes to blink. This moment is called cosmic inflation, and it is one of those ideas that sounds like science fiction until you learn that it is our best explanation for why the universe looks the way it does. Inflation is the cosmic equivalent of someone accidentally turning the expansion dial to maximum and then scrambling to switch it back before the whole thing flew off the cosmic countertop. The story begins with a peculiar kind of energy, something that did not behave like the forms of energy we see today. It did not glow. It did not flow. It did not even smear itself around like heat or light. Instead, this energy clung tightly to space itself, pushing outward with a kind of relentless enthusiasm. When physicists describe this energy, they often make it sound like a misbehaving ingredient in the recipe of reality, something that was only supposed to sit quietly in the background, but instead decided to take over the entire bowl. Once this energy became dominant, space-time responded by stretching faster than anything we can physically imagine. What had once been tiny became enormous. What had once been cramped became spacious. And what had once been chaotic became surprisingly smooth, like someone had taken the wrinkles out of the infant universe with a cosmic iron. Now, the fun part is that inflation did not necessarily happen in a uniform, one-time-only way. Some theories suggest that inflation might be more like a chain reaction continuing in some regions even after it stopped in others. Imagine a bowl of bread dough that begins rising all at once, but instead of rising evenly, certain pockets expand faster and faster, climbing over the edges while other pockets settle down and become calm little loaves. That is one way of imagining the multiverse, a cosmic bakery where dough never stops rising in some places, producing endless pockets of space-time that balloon into separate, self-contained universes. In this analogy, our universe is just one loaf that formed when inflation stopped in our region. Once the inflationary energy dissipated here, space cooled enough to let particles, atoms, stars, and eventually people appear. But beyond our settled dough, the rising continues elsewhere. Those expanding pockets create new universes, each sealed off from the others by the speed of their expansion. They grow so quickly that no signal, no light, no particle could ever travel from one to another. They stretch themselves away at such extraordinary speeds that, from the perspective of any inhabitant inside one, the rest might as well not exist at all. To understand why inflation might generate multiple universes, picture the inflationary energy as a kind of unstable cosmic yeast. It expands wherever it remains active, shaping enormous new spaces as it does. But in some pockets, it fizzles out. The moment the yeast stops bubbling in a region, that region stops expanding at runaway speed. It becomes a calmer, more orderly place, and that calmer place becomes a universe. Meanwhile, elsewhere, the yeast keeps working, and new bubbles of reality keep rising and rising and rising. If there were a cosmic baker watching all this unfold, they would probably sigh, wipe their metaphorical hands on a flour-dusted apron, and mutter something like, "I did not ask the dough to do that." Another striking implication of this idea is that each universe might come with its own physical constants. When inflation ends in a particular bubble, the final properties of that region, such as the strength of gravity or the mass of a particle, might crystallize differently. It is like taking dozens of batches of dough made from slightly different ingredients and letting each one rise in its own bowl. Some might turn out dense and chewy, others light and airy, others totally inedible, and at least one might puff up so aggressively that it blasts the mixing spoon across the kitchen. The multiverse, in this sense, could be a collection of universes that formed under different cosmic baking conditions, each with its own flavor of physics. The fascinating part is that inflation is not just a whimsical idea tossed around because it sounds poetic. It solves several real puzzles about our universe. It explains why matter is spread out so evenly across the cosmos. It explains why regions that should never have communicated with each other somehow ended up with matching temperatures, as though they had an early chat before being flung apart at impossible speeds. And it explains why space is so close to perfectly flat, stretching out like a vast table instead of curving in on itself. Inflation wipes away the irregularities, straightens out the geometry, and sends everything flying outward in a clean, inescapable rush. But the truly mind-bending part is this. If inflation naturally creates pockets where expansion ends and pockets where it continues, then the existence of multiple universes is not just possible, it might be the natural outcome. The cosmos might be perpetually kneading itself, generating new pockets of space-time like a bakery that refuses to close, no matter how many batches it has already produced. In our expanding dough bubble, we have stars, planets, life, thought, and curiosity. In other bubbles, who knows? Perhaps physics runs differently. Perhaps nothing recognizable forms at all. Perhaps strange structures arise that do not even have names in our language. But whether or not we ever learn what goes on in those other pockets, the idea that inflation might endlessly create them paints a picture of reality that is far bigger than our single universe. It suggests that we are living inside one loaf in an infinite, ever-rising cosmic kitchen, unaware of the countless others, but no less real because of them. And in that sense, cosmic inflation is not just a piece of physics. It is a story about how reality might continually reinvent itself, expanding beyond imagination while quietly sprinkling new universes into existence, like flour drifting in the air of a very busy, very enthusiastic bakery. If the multiverse really is a cosmic kitchen full of rising dough bubbles, then every now and then you have to wonder what happens when two of those bubbles drift close enough for their edges to touch. It is a strange thing to imagine, because we are used to thinking of our universe as the entire show, the full stage, the whole theater. But if reality is instead a vast backstage full of inflating cosmic pockets, then our universe is only one actor wandering across one small corner of an enormous set. And actors are not always great at watching where they are going. Sometimes they bump into scenery. Sometimes they walk into each other. And in the grand drama of inflationary theory, universes can do the same, except the collisions are not clumsy encounters, so much as spectacular meetings between colossal domains of space-time. The metaphor most physicists reach for is the soap bubble, not the kind drifting lazily from a child's wand on a warm afternoon. Those are far too delicate and polite. Instead, imagine two enormous bubbles made of space-time itself, floating in a silent backdrop so empty it makes darkness look crowded. These bubbles are not solid. They do not have walls you can touch. Their boundaries are more like shifting gradients, the invisible regions where one set of physical rules transitions into another. From the inside, you would never know that your cosmic bubble even had a boundary at all. Everything feels infinitely open and smooth, like a vast stretch of sky with no end. But from the outside, in the conceptual picture inflationary theorists love to paint, these bubbles drift. They expand. They wander through the inflationary landscape like half-awake giants who have not realized how large their footsteps really are. Each giant bubble grows so quickly that it pushes everything else away, but not always fast enough to guarantee eternal solitude. Just as real bubbles occasionally bump on the surface of a sink full of suds, these cosmic bubbles can drift into proximity, their boundaries pressing together in a moment that is both graceful and utterly enormous. A collision between universes would not look like two billiard balls striking each other. It would be more like two slowly expanding membranes making first contact. The touching point would not be a simple dot. It would be a spreading area, a kind of cosmic bruise blooming across the boundary as the surfaces adjust to one another. In inflationary theory, these points of contact could produce intense bursts of energy, something like a shock front rolling through the region of the collision. Not a violent explosion in the sense we experience explosions, but a vast release of stored expansion energy, transforming into something new as the boundaries reshape. Inside one of those universes, this encounter might play out in subtly eerie ways. You would not see another cosmos barreling toward you like a bright ball in the night sky. Instead, the influence of the collision would appear as a kind of distortion creeping across your universe's early stages. It would leave behind a pattern, a faint cosmic birthmark placed long before galaxies ever formed. Our own observable universe might hold such a pattern, though searching for it is like trying to find a faint fingerprint pressed gently into the fabric of the cosmic microwave glow. Whether such a mark exists, however, is not the focus here. What matters is understanding how inflation provides the stage on which such collisions could occur at all. During eternal inflation, new bubbles form in a rapidly expanding background. Each bubble is a self-contained universe, but that background is not infinite in the easy sense. It does not stretch out peacefully like a calm ocean. It is roiling, dynamic, constantly spawning new pockets, while older ones continue to swell. Because these bubbles grow at extraordinary rates, collisions are not guaranteed, but neither are they forbidden. Over unimaginable stretches of time, the inflationary sea produces so many bubbles that the chance of two eventually brushing against each other becomes not only possible, but likely. The drama of the collision hinges on perspective. From the outside, if there even is an outside in any meaningful sense, it is a simple geometric encounter. Two bubbles drift close, their boundaries meet, a merging region forms. But from the inside, for any beings living within one of these bubbles, the event would be beyond comprehension. To them, space-time simply is what it is. The collision would not resemble two giant spheres touching, but rather an unexpected alteration in the uniformity of their universe's earliest conditions, a kind of cosmic ripple, or a faint asymmetry in the distribution of matter. The universe would carry the memory of the collision without ever revealing the true shape of the encounter. The metaphor of oblivious giants walking into each other captures the mood perfectly. These universes are not malicious. They are not even aware. They simply expand according to the rules set by inflation, stretching outward until eventually their paths cross. The collision is not a conscious act, but a natural consequence of endless growth. Two enormous beings roaming the darkness without ever looking down, and at some unpredictable moment, their vast limbs graze one another, sending out shock waves that reshape the regions they touch. Importantly, a universe collision does not necessarily destroy either universe. Depending on the nature of the contact, the encounter could be gentle, like two giants brushing shoulders as they pass. Or it could be energetic, imprinting structural changes across the bubble interiors. The outcome depends on the speed, angle, and inflationary properties of the bubbles involved. Details no observer inside either universe could ever directly perceive. But the idea itself, the possibility of such colossal interactions, is what makes inflationary theory so mesmerizing. It transforms the cosmos from a solitary, self-contained world into part of a larger, ever-changing landscape. It invites us to imagine our universe as one drifting bubble among countless others, all expanding, all exploring the darkness, all occasionally bumping into one another in encounters so vast and so gentle that only the universe itself can remember them. In this chapter, the focus is the dance of these drifting giants, how they arise, how they wander, and how their collisions become the quiet signatures written into the earliest fabric of a universe's history. Each bubble moves through an inflationary sea that never rests, a place where the delicate brushing of boundaries can transform entire cosmic destinies, even though from the inside the sky remains calm, silent, and seemingly alone. If two universes ever drift close enough for their edges to meet, the encounter does not unfold in a way that resembles anything familiar from our everyday world. There is no great clatter of colliding objects, no thunderous crash echoing across the void, no warning lights blinking in alarm. Instead, everything hinges on a strange and subtle place, the boundary. That boundary is not a hard edge or a physical wall. It is more like a shifting frontier where the rules of one universe give way to the rules of another. Think of it as the cosmic equivalent of a property fence drawn in invisible ink, one meant to say, "Do not touch." Yet the cosmos drifts right through it anyway, with the relaxed confidence of something that has never once asked permission. To picture this boundary, imagine a thin, flexible membrane that marks where one bubble of space-time ends and another begins. Inside your universe, everything flows according to familiar laws. Light follows predictable paths, energy behaves as expected, matter interacts in the usual ways. But near the outermost edge, far beyond anything we could ever hope to observe, you would reach the region where the underlying structure of space-time begins to shift. It is not that your universe suddenly looks different. It is more like the subtle change in air pressure when you walk from one climate-controlled room into another. Everything works, but something in the background feels slightly off, as though some cosmic architect forgot to smooth out the transition. When another universe comes drifting close, its boundary pushes through that same invisible frontier. And suddenly, two sets of rules, two deep cosmic blueprints, are forced to share a tiny region where neither fully dominates. This is the zone physicists find most intriguing, because it is here that energy can behave in ways that defy intuition. If your universe and the approaching universe both carry different configurations of inflationary energy, those energies can collide like opposing ocean currents, creating chaotic disturbances that ripple across the contact surface. not destructive in the cinematic sense, but potent in the way they rearrange space-time. Some theories suggest that the energy stored in each universe's boundary could be released when they meet. It would not be an explosion as we understand explosions, but a release of pressure, like the sudden whoosh you hear when two sealed compartments are open to each other. This release would create a kind of cosmic shock front that moves through the region of overlap. Inside a universe, that shock front would appear as a subtle modification to the earliest distribution of energy, not something a person could see with their eyes, but something imprinted into the deep fabric of the cosmos, like a faint scar left by an event that happened long before stars ever existed. The notion of boundaries meeting might make you imagine a collision that happens in a single moment, but in reality, it is more like a slow, expanding interface. As the universes continue to grow, the region where they touch widens. The boundary, once a clean dividing line, becomes a warped and turbulent frontier. Energy in this region tries to settle into a stable configuration, but because two incompatible cosmic rulebooks are overlapping, the process can be messy. Imagine two musical instruments trying to play different songs at the same time, not violently clashing, but struggling to find harmony in the shared space. The resulting melody, if one can call it that, becomes encoded into the expanding universe. Part of what makes this boundary so fascinating is the possibility that it might produce structures or imprints that persist for billions of years. The energy transitions occurring there could alter how matter forms in the early cosmos. They might shape patterns in the deep background radiation. They might even influence the large-scale geometry of the universe, creating a slight tilt or asymmetry that otherwise has no explanation. All of these effects would be faint, subtle, and incredibly ancient, like fossils in the bedrock of space-time itself. And then there is the stranger idea that the boundary between universes could act as a channel, a place where fields or energies briefly interact, not enough to merge the universes or allow matter to flow between them, but enough for the collision to leave behind a signature, a reminder that the cosmos once brushed past an equally vast neighbor. It is the cosmic equivalent of two ships passing in the night and scraping hulls just slightly, leaving behind a mark that future explorers puzzle over without ever seeing the other ship. Humorously, one might imagine that the cosmos tried to put up an invisible "do not touch" sign at each universe boundary, a polite suggestion that these enormous bubbles should keep to their own cosmic lanes. But universes, lacking any sense of social etiquette, drift more like daydreaming travelers than rule-following citizens. They expand wherever inflation drives them, unbothered by boundaries meant to separate them. And when they finally meet, they ignore every cosmic instruction manual and proceed to mix energies in ways that challenge our understanding of what separate really means. Yet even with all this complexity, the collision boundary is not chaotic in a destructive way. It is more like a negotiation between two enormous systems settling into a new configuration. The energies exchange subtle influences, the boundaries curve and shift, and the collision zone expands outward with time. Inside each universe, life goes on. Stars ignite, planets gather dust, chemistry takes root, completely unaware that their reality once brushed shoulders with another. The beauty of this concept is that it shows how gently colossal events can unfold when the stage is made of space-time itself. The boundary between colliding universes is not an apocalyptic battlefield, but a delicate frontier where two realities meet, reshape, and then drift apart into their separate destinies. And all the while, the cosmos casually ignores the very idea of do not touch, proving once again that the universe has never been particularly good at following directions. If universes can brush against each other like wandering giants, leaving behind ripples in the boundary where they touch, then the obvious question becomes, could we actually see any evidence of such an encounter from inside our own cosmic bubble? It is one thing to imagine universes nudging each other in the darkness, but it is an entirely different challenge to detect the faint whispers of such an event billions of years after it happened. Yet if a collision ever occurred in the early stages of our universe's formation, it might have left subtle marks, cosmic fingerprints pressed into the sky long before stars, galaxies, or planets had even been dreamed of. These signs would not be glaring or dramatic. They would not appear as glowing scars or cracks across the heavens. Instead, they would resemble gentle bruises, faint irregularities in the cosmic background that make scientists pause and say, well, that is odd. The place to search for these marks is the cosmic microwave background, the faint afterglow of the earliest era of our universe. It is the oldest light we can see, the quiet echo of a time when everything was so dense and hot that the cosmos glowed like a furnace. When the universe finally cooled enough to let light travel freely, this glow spread outward, stretching and softening until it became the delicate microwave radiation that now coats the entire sky. It is as though the universe left behind a baby photo of itself, and cosmologists have been analyzing it ever since, zooming in on every pixel in hopes of catching a glimpse of something unusual. A universe collision, if it happened, might have imprinted itself onto this ancient light. One of the most discussed possibilities is the presence of strange circular patterns, regions of slightly different temperature that do not quite match the random fluctuations expected from normal cosmic evolution. Some of these circles might appear as cooler patches, like the universe rolled over one morning, looked in the cosmic mirror, and muttered, "Where did that come from?" These cold spots would not be icy in the everyday sense. They are simply areas where the energy distribution ended up lower than average, a tiny dip in the warmth of the background glow. But their presence, if clearly linked to a collision, would be profound. A direct indication that our universe once nudged against another during its earliest moments. The reason a collision might create such a cold patch has to do with how energy is distributed when two cosmic domains meet. The shock front produced at the collision boundary can cause a localized shift in temperature, a kind of cosmic bruise that remains frozen into the expanding universe. As space stretches and the microwave glow cools, that bruise stretches with it, ballooning into an enormous region that modern telescopes can observe. It becomes a vast, softly defined circle, too large to miss, too strange to ignore, yet too subtle to conclusively interpret without years of analysis. Scientists have indeed found curious cold regions, including one famously oversized cold area that researchers continue to debate. Was it caused by a universe collision, or by something more mundane like a statistical fluke? No one can say for sure. The universe, being the mischievous storyteller it is, rarely hands us straightforward answers. Another potential signature lies in asymmetry. If a collision occurred, it might warp the symmetry of the sky in a way that cannot be explained by internal physics alone. Imagine the universe as a drumhead that was once struck slightly off-center. The vibrations would ripple outward unevenly, creating a pattern that forever remembers that first asymmetric push. In the same way, a universe collision might leave our cosmos with a gentle tilt, a faint directional preference baked into the earliest distribution of energy. This kind of anomaly would not look dramatic to the naked eye, but sophisticated measurements could reveal that one region of the sky behaves subtly differently than another. It is the cosmic equivalent of noticing that one side of the bed seems lower than the other, even if you cannot see the difference at a glance. Yet another possible signature involves unusual polarization patterns in the microwave background. When light scatters in the early universe, it can become polarized, its waves oriented in specific directions. A collision might create a distinctive swirl or alignment pattern, something like the fingerprint left by a hand pressed briefly against soft clay. Cosmologists scrutinize these patterns with intensity, hoping for that one telltale swirl that cannot be explained by anything inside our universe. If such a pattern were found and confirmed, it would be one of the most astonishing discoveries in the history of science, a sign that our universe carries the memory of touching another. There is also the possibility of subtle distortions in the distribution of galaxy clusters. If the shock of a collision rippled through the early cosmos, it might have influenced where matter gathered as gravity began pulling everything together. This effect would be extremely faint, something only visible in enormous statistical surveys, but it could reveal an unusual alignment or concentration of matter in one direction. It is as though the universe, still half asleep in its infancy, leaned slightly to one side because of a nudge it received long before galaxies existed. And through all of this, the most charming aspect is the idea that our universe might be walking around with bruises from an ancient encounter it never fully understood. Not catastrophic scars, not dramatic wounds, but little marks, quirky imperfections that hint at a much larger, much stranger history. If universes could talk, ours might insist the bruises are nothing, really, just a childhood scrape from when it wandered too close to the neighbor's bubble. Nothing to worry about, no big deal. Still, those faint marks could be the key to proving that our universe is not alone. In this chapter, the focus is on these delicate signs, the subtle fingerprints, faint bruises, gentle distortions that could reveal a moment of contact with another universe. They whisper of a cosmos more connected, more dynamic, and far more surprising than anyone imagined, leaving us with the tantalizing possibility that our sky holds memories written in patterns older than time itself. When two universes brush against one another, The event is not limited to faint temperature quirks or delicate imprints hidden in ancient radiation. There is another layer to the drama, something deeper, stranger, and far more theatrical. It is the way space-time itself might react. If universes are colossal bubbles of space-time floating in a vast inflationary ocean, then their edges carry not only energy, but also curvature. Push on that curvature even slightly, and space-time does what any flexible material does when stressed. It stretches, bends, and occasionally quivers like it is holding in a complaint. And honestly, who can blame it? Even space-time gets cranky when squeezed. To understand gravitational distortions from a collision, you first need to imagine space-time as something more than an empty grid. Instead, picture it as an enormous sheet made of the most elastic fabric imaginable, something that stretches effortlessly yet remembers every tug. Gravity in this picture is what happens when mass presses down on the sheet, creating dips and curves. But if another universe comes drifting close, the pressure does not come from ordinary mass. It comes from the inflating, expanding bulk of an entirely different space-time bubble. When that bubble presses against ours, it is not a local dip, but an enormous compression wave, something so sweeping that it reshapes the sheet on a cosmic scale. The first effect of this pressure would be a large-scale deformation of curvature. Think of it as space-time being nudged sideways, like someone pushing gently on the side of a trampoline. The fabric responds by bending, but not all at once. The distortion spreads across the sheet, smoothing out as it travels. Inside a universe, such a shift could cause subtle anisotropies, directions of space that behave differently than others, even before matter had a chance to settle. It is as though space-time flinched from the contact and took a while to relax again, leaving behind a lasting hint of where it was pressed. But the most fascinating and dramatic possibilities involve ripples. When the boundary between universes releases energy, that energy can manifest as disturbances that travel through space-time, much like waves on water. These waves are more than just gentle tremors. They are gravitational ripples, fluctuations in the curvature itself. They do not need matter to carry them. They move through space-time purely by bending and unbending it, propagating outward with the eerie silence of something that does not require air, sound, or anything material to spread. It is the universe's version of a full-body shiver. The ripples from a universe collision would be different from the gravitational waves we observe from merging black holes or collapsing stars. Those events create sharp, intense ripples, brief, powerful spikes in curvature that fade as they radiate outward. A universe collision, however, might create something far broader and slower, a kind of deep gravitational hum that lingers across enormous scales. Instead of a quick burst, it would resemble a long, resonant chord played on the grandest instrument imaginable. The entire universe would be the audience, whether it realized it or not. Inside such a universe, the effects of this gravitational hum could be subtle but pervasive. It might influence how space expands in different directions, creating regions where expansion was slightly faster or slower. It might alter the primordial distribution of gravitational potential, gently nudging matter towards certain areas before galaxies even had a chance to form. It might even create faint directional preferences, cosmic habits almost, that persist long after the original ripple faded into silence. One way to visualize this is to imagine space-time as a massive mattress. Normally, placing objects on it produces neat dimples, stars, planets, and black holes sitting comfortably in their curved pockets. But now imagine someone presses a giant knee into one corner of the mattress. The entire surface tilts, however slightly, and all the objects shift just a little bit in response. They do not roll dramatically, but they settle into new positions, reflecting that initial push. That tilt, that subtle change in balance, is the sort of gravitational shift a universe collision could imprint across its interior. And then there is the possibility of localized wrinkles. When two expanding bubbles press against each other, the boundaries might not press smoothly. They could bunch, buckle, or fold in complex ways before smoothing out. These folds in space-time could propagate inward as complex gravitational disturbances, forming patterns that echo the chaotic interaction that birthed them. And such wrinkles would not leave visible scars, but they could influence how clusters of matter formed later on. It is like giving space-time a shove and creating tiny creases that never fully iron out. The truly humorous part of all this is that space-time, majestic as it seems, behaves a lot like an overworked rubber sheet. Squeeze it too hard, and it springs back in protest. Nudge it unexpectedly, and it sulks with slow undulations that take billions of years to fade. For all its cosmic dignity, space-time is surprisingly expressive when you stress it, almost as though it throws a tantrum on wavelengths too large for humans to notice directly. If such gravitational distortions remain imprinted in our cosmos, they would reveal themselves only through painstaking observations, not by dramatic shifts or gaping holes in reality, but by delicate quirks in how galaxies cluster, how light from distant stars bends, or how expansion varies across directions. Scientists search for these hints not because they expect a clear, obvious sign, but because the universe tends to whisper instead of shout. A gravitational bruise, a directional drift, a peculiar alignment. These might be the quiet echoes of a moment when space-time was squeezed by something unimaginably vast. And that is the wonder of this chapter, that a collision between universes is not merely a meeting of boundaries or a swap of energy signatures. It is a reshaping of space-time itself, a moment when the foundational fabric of reality ripples, shivers, and responds. Even if the universe tries to hide the disturbance beneath billions of years of expansion, those ancient gravitational murmurs might still hum through the cosmos, telling a story only the most careful listeners can hear. If two universes ever brushed against each other, the most bewildered witness would not be space-time itself, though it certainly has its dramatic moments. The real confusion would happen at the level of matter, the building blocks of everything that eventually becomes planets, organisms, cities, telescopes, and the minds asking these questions in the first place. Matter is a wonderfully predictable thing under normal circumstances. Atoms follow rules so well that chemistry textbooks barely need to scold them. But toss them into a scenario where another universe's boundary sweeps through their environment, and suddenly they are like startled tourists stepping off a train and realizing none of the signs match the guidebook they brought. To understand this confusion, imagine matter in its earliest form, simple particles drifting through the newborn cosmos. In a universe that has never been touched by another, these particles settle into a familiar pattern. They dance to the rhythm of their own physics, forming clouds and clusters according to temperature, pressure, density, and the subtle tugs of gravity. But insert the disturbance of a universe collision, an enormous shift at the boundary that ripples inward, and the earliest matter finds itself confronted with conditions it was never designed to interpret. It is like arriving in a foreign city where the traffic moves backward. Every street loops mysteriously into itself, and the map in your hand insists that the nearest cafe is directly beneath your feet. One of the first changes matter might encounter is a shift in the distribution of energy. When two universes meet, the energy released at the boundary can wash into the interior, altering temperature gradients and creating unfamiliar conditions in regions that were previously uniform. Particles that expected a steady environment suddenly feel a subtle push or pull that mildly redirects their path. They might cluster slightly earlier or disperse slightly differently than they otherwise would. It is not catastrophic. No atoms combust from shock, but the early matter behaves with a hint of confusion, like someone turning a corner and realizing the street they thought they were on has mysteriously rearranged itself. Now, matter in the early universe is not delicate. These particles are not fragile snowflakes waiting to melt at the slightest hiccup. They are hardy little bundles of quantum energy, able to withstand conditions so extreme they make volcanoes look like well-tempered teapots. Even so, they are sensitive to the rules under which they operate. If the collision introduces a wave of altered gravitational potential, matter will respond. If the collision creates a directional preference in how energy flows, matter will drift accordingly. The atoms do not panic. They simply try to read the new cosmic map with whatever instructions reality hands them. But because the collision may imprint unusual gradients into the universe, the early atomic travelers end up following paths that differ ever so slightly from their original routes. These tiny deviations matter, literally. In the early universe, small shifts in matter distribution can snowball into larger structures. A slight compression in one region can eventually become the seed of a cluster of galaxies. A slight rarefaction elsewhere can lead to an expanse nearly empty of matter. If the universe had never brushed against another, these patterns might have been smoother or more symmetrical. But with the collision, they bear subtle quirks, like the faint accent you pick up after spending too much time in a foreign country. Another fascinating possibility arises from how fields interact with matter. Every particle in the universe is tied to fields: gravitational fields, electromagnetic fields, quantum fields that underpin their very existence. If the boundary of another universe injects disturbances into these fields, even temporarily, matter may behave differently in that region. Particles could oscillate slightly out of sync. Recombination, the moment when electrons settled into orbits around nuclei, could occur with tiny variations. Again, the atoms are not falling apart or rewriting chemistry. They are simply adapting to the peculiarities introduced by the collision, like tourists squinting at street signs and muttering, "I swear this is not how the map said this was supposed to work." One especially intriguing effect involves the potential creation of unusual density contrasts. When matter experiences a passing wave of altered space-time curvature, it can get gently squeezed or stretched. Imagine a cosmic breeze nudging particles closer together in one area and pushing them apart in another. These variations travel outward, mixing with the universe's natural fluctuations. The result is a landscape where matter forms a slightly unusual pattern, a cosmic quilt stitched with the faint fingerprints of the collision. Billions of years later, galaxies might gather in ways that subtly remember those early nudges, like architectural choices shaped by city planners whose names no one recalls. But perhaps the most charming way to envision matter during such an event is to picture atoms as earnest travelers. Imagine a proton standing at the edge of the primordial soup, happily obeying the laws it has always trusted, when suddenly a gravitational ripple from the collision sweeps through. The proton hesitates, recalculates, and then continues onward with the resigned patience of a tourist who has just discovered that the metro line they were following now goes in the opposite direction on weekends. Nothing breaks, nothing implodes. Matter simply adapts, because adapting is what matter has always done best. Of course, the influence of a universe collision would be strongest in the earliest moments, when matter had not yet formed complex structures. Once stars ignite and galaxies swirl into being, these ancient influences become increasingly faint, stretched and diluted by the relentless expansion of space. But they do not vanish completely. Somewhere in the arrangement of galaxies, in the subtle alignments of mass, and in the fine textures of cosmic structure, there might exist tiny clues, echoes of a moment when matter behaved like a traveler in unfamiliar territory. In this chapter, the focus rests entirely on those early particles, how they drift, how they adapt, how they reorganize themselves in the presence of a cosmic disturbance. Their reactions are not dramatic, but quietly profound, shaping the grand architecture of the universe through minor interactions with a larger, stranger event. Just as every journey reshapes the traveler in small ways, a universe collision reshapes matter, leaving the vast cosmos with patterns that whisper, "Once, long ago, reality had an unexpected visitor." If a collision with another universe sounds like the kind of thing that should leave our cosmos shattered, scattered, or dramatically rewritten, it is worth remembering that the universe is surprisingly sturdy. It has been flung, stretched, compressed, and heated beyond anything humans experience outside of very determined cooking experiments, and yet it persists with unwavering determination. Still, the idea of our universe surviving a brush with another raises fascinating possibilities. Not because such an event would tear reality apart, but because it could quietly reshape the cosmic blueprint, the way a renovation crew might show up at your house unannounced and replace half the walls, install a spiral staircase, and leave a note reading, "We think it looks better this way." To understand how such a renovation could unfold, imagine our universe as a vast, evolving structure whose early blueprint is encoded in the distribution of matter, the curve of spacetime, and the background fields that permeate everything. This blueprint is not rigid. It evolves over time, especially in the universe's earliest stages before stars and galaxies existed. A collision during these formative phases would not smash things apart, but influence how they assemble, leaving behind a remodeled structure that billions of years later seems perfectly normal to us, because we never saw the original plan. One of the first ways our universe might adapt to such an encounter is through adjustments in its large-scale geometry. The collision could introduce a directional preference, a subtle tilt, or a lingering asymmetry. These changes would not feel dramatic from the inside. You would not wake up one morning and notice that space is slightly slanted, the way you might notice a coffee table listing to one side. Instead, the entire fabric of the universe would follow the new geometry seamlessly, growing outward with that small nudge baked into its structure. It is the cosmic equivalent of discovering that your house was built on a gentle slope, but realizing it never mattered because everything inside adjusts naturally. Another way the universe might be reshaped is through the distribution of its foundational energy. During a collision, energy from the boundary interaction could flow inward, subtly altering how fields settle. These fields, the deep scaffolding on which all particles and interactions depend, determine the behavior of everything that follows. A change in the early configuration of these fields might shift the fine details of how matter organizes, not enough to break the universe, but enough to give it a slightly different character. Perhaps the clusters of galaxies end up more densely packed in one direction. Perhaps voids grow a bit more prominent somewhere else. Maybe the average distribution of structures takes on a gentle anisotropy, an echo of that ancient, invisible nudge. Such modifications would not feel chaotic. The universe is remarkably good at smoothing things out. Expansion works like the world's most patient decorator, stretching, diluting, and calming the early chaos until everything looks orderly again. But beneath the surface, the cosmic renovation remains. It is why cosmologists sometimes describe the effects of a universe collision as residual signatures. These signatures are not obvious scars. They are more like architectural quirks, a door frame that is ever so slightly off-center, a staircase that is one step shorter than expected, a decorative archway that hints someone once made a different design choice. Beyond geometry and energy distribution, the collision might also influence the overall rate or direction of cosmic expansion. A passing universe could impart a subtle push, not enough to derail the expansion entirely, but enough to alter its flow. Imagine space expanding like dough rising in a pan. collision is the gentle tap that makes one side rise a little differently. Over billions of years, that small difference could grow into a measurable tilt, a cue that the expansion was once shaped by external forces. For us inside the universe, this shaping would be invisible, just another cosmic constant we assume has been there since the beginning. But perhaps the most striking possibility is that a universe collision might contribute to the emergence of structural diversity. Without such an encounter, the universe might have developed with greater uniformity. Instead, a collision introduces variation, a touch of asymmetry that gives the cosmos a slightly more textured interior. It is like walking into a renovated apartment and noticing that one wall has an unusual curve, not a flaw, but a unique feature created by the builder's decisions long before you arrived. If life arises billions of years later, and apparently it did, since you are here reading this, that life will grow up inside a universe already shaped by these ancient influences. To us, everything feels natural. The distribution of galaxies, the patterns in cosmic background light, the gravitational architecture that binds matter together. We do not see the original layout, so we have no reason to suspect alterations were ever made. It is only through the careful scrutiny of cosmologists, those cosmic detectives digging through the sky's oldest layers, that we might uncover clues of a remodel we never signed off on. And yet, the most delightful aspect of this idea is that our universe survives such a cosmic renovation without complaint. It adapts. It incorporates the changes. It continues its expansion as though nothing unusual happened. This resilience speaks to the stability of the underlying physics, the way space-time, matter, and energy naturally settle into coherent structures even after disturbances. The universe does not crumble when nudged. It improvises gracefully. If universes carried paperwork, ours would have a file thick with unapproved modifications, but it does not mind. It wears its adjustments like character traits earned through extraordinary experiences. In this sense, a universe collision becomes not a catastrophic event, but a formative one, an unexpected brush with another reality that helped shape the cosmos into the sprawling, structured, beautifully complex expanse we inhabit. This chapter is the story of that cosmic renovation, the subtle reshaping of geometry, the quiet redirection of energies, the long-lasting architectural quirks imprinted into the universe's structure. It reminds us that even on the grandest scales, reality is not static. It evolves, adapts, and grows, sometimes with a little help from a visitor who wandered much closer than expected. Up to now, the story of universe collisions has been surprisingly gentle. Most scenarios lean towards subtle distortions, quiet imprints, a few cosmic bruises, and the occasional unplanned renovation. But if we step into the realm of extremes, the kind of possibilities that make theoretical physicists pause, sigh, and reach for stronger coffee, then we must consider a more dramatic question. Could a collision between universes wipe one of them out entirely? Could it, in some unimaginable circumstance, trigger an event so fundamental that the universe does not get remodeled, but instead gets replaced? In other words, what would it look like if the cosmos hit the metaphorical factory reset button? To imagine such a scenario, picture our universe as a stable configuration of space-time, energy, and laws. The stability arises from deep fields and vacuum states that determine how everything behaves. But these states are not necessarily permanent. They sit in what physicists call vacuum configurations, which are essentially energy levels in the fabric of space-time itself. Our universe occupies one particular configuration, a low-energy valley in the landscape of possibilities. If left undisturbed, it can remain there indefinitely, expanding, cooling, forming stars, building galaxies, and occasionally producing creatures who ask questions about cosmic doom. But now imagine a universe with a boundary that carries a vastly different vacuum state drifting toward ours. If that incoming universe represents a deeper, more stable configuration, a valley lower than the one we currently inhabit, then its boundary could act like a wave of new physics sweeping through our reality. As it passes, it could trigger a transition in the vacuum structure itself, forcing our universe to switch to the new state, whether it feels ready or not. If space-time could talk, this would be the moment it exclaimed, "Hey, I did not agree to this update," right before everything changed anyway. This process is known in theoretical circles as vacuum decay. The name makes it sound like space-time went bad in the back of the cosmic fridge, but the event is far more dramatic. If triggered, vacuum decay would not merely rewrite small details. It would overhaul the entire framework, the strengths of forces, the masses of particles, the speed of light, the behavior of energy, maybe even the dimensional structure itself. Imagine every physical constant suddenly reassigned new values, as if the universe were being auditioned for a very different show. Chemistry would not survive. Atoms would not survive. Even the notion of survive would become irrelevant, because the rules governing existence would be replaced wholesale. The wave of new vacuum state would expand outward at extraordinary speed, not the speed of a shock wave or explosion, but the speed of space-time transition itself. There would be no warning, no visible flash, no dramatic sound. The boundary would move silently, rewriting everything it touched. One moment the universe is humming along with familiar physics. The next, its entire rulebook has been swapped out for a version no structure inside it can support. It is the ultimate cosmic reboot, except nothing that existed before the reboot carries over. Not even the save files. This might sound terrifying, but the humor buried in it, if one can call it humor, is that such an event would be perfectly efficient. There is no mess, no lingering debris, no cosmic cleanup crew required. The transition is instant and absolute. In an almost comically bureaucratic way, it is the universe performing the ultimate factory reset. wiping all settings, clearing all data, and returning space-time to whatever configuration the new vacuum state demands. If there were a cosmic help desk, it would cheerfully remind you that this action cannot be undone, and all previous reality will be permanently lost. But for all its extremity, this kind of total destruction is not the expected outcome of a universe collision. It is merely the fringe case, the conceptual outer boundary of what is theoretically possible. Most collisions would not involve such incompatible vacuum states. The universes likely would not carry the exact combination of properties required to destabilize each other. Collisions generally imprint, nudge, reshape, or slightly modify. They do not typically annihilate the entire structure. But in the landscape of speculative physics, the vacuum decay possibility sits quietly in the corner, raising its hand now and then to remind us that under certain conditions, the cosmos could indeed overwrite itself. Even in more moderate extreme scenarios, destruction would still be profound. A collision could theoretically inject enormous amounts of energy into a region, heating it so intensely that matter cannot settle into stable structures. In these cases, destruction does not mean wiping out space-time, but rather preventing any meaningful complexity from forming. Galaxies would fail to coalesce. Stars would remain scattered, too perturbed to ignite. The universe would become a vast, featureless plane of radiation and particles in perpetual agitation, not shattered, but sterilized. Another dramatic outcome involves the possibility of creating new regions of space-time that peel off from the collision zone. Instead of destroying one universe, a collision could spawn entirely new pockets of reality, like branches sprouting from a tree when two growing limbs collide. In this scenario, the destruction is less absolute and more transformative. The old structure becomes the seedbed for something new, altered perhaps beyond recognition, but not erased. Of course, any form of cosmic destruction, whether total or partial, remains deeply speculative. We do not have observational evidence of universes annihilating each other, nor do we have a way to test such scenarios experimentally. They are conceptual tools, reminders that the multiverse, if real, might host events far stranger than what our limited cosmic bubble has experienced. And yet, for all the frightening implications, there is something oddly calming about pondering these extremes. They highlight the resilience of our universe, the improbability of catastrophic encounters, and the fact that existence persists because conditions allow it to. The possibility of a cosmic factory reset is a reminder of how delicate and extraordinary our reality truly is, perched beautifully in its own vacuum valley, stable enough to support galaxies and life, quietly expanding, and apparently not scheduled for any surprise reboots. In this chapter, we explored the furthest edge of possibility, how a universe might be destroyed or overwritten entirely. It is the story of ultimate instability, of physics rewritten at the deepest level, and of the cosmos reminding us that while it prefers subtlety, it is fully capable of theatrical extremes. Thankfully, those extremes remain theoretical musings rather than looming threats. cosmic thought experiments that help us appreciate the stability of the universe we call home. Not all universe collisions need to resemble high-stakes cosmic drama. In fact, one of the most charming possibilities in the multiverse narrative, and certainly the least anxiety-provoking, is that two universes could make contact so gently that they barely notice each other at all. No sparks, no scars, no dramatic shifts in physics, just a brief, polite brush of boundaries, something so mild it feels less like a collision and more like two shy cosmic entities exchanging awkward handshakes before quietly drifting apart and pretending the whole thing never happened. To picture a gentle merger, imagine two enormous bubbles of spacetime expanding calmly in the inflationary sea. Their boundaries drift outward, smooth and uniform, until they touch with all the subtlety of a feather landing on a cloud. In this soft contact scenario, the energies of the two universes meet at such compatible levels that neither is forced to reorganize its internal structure. Instead, the boundaries simply mold slightly around each other, adjusting like soft clay before settling back into their usual shape. It is the cosmic equivalent of brushing past someone in a narrow hallway and both of you muttering, "Sorry, my fault," even though neither of you was truly at fault. What makes this scenario possible is that the properties of different universes need not always be dramatically different. If two universes arise from similar inflationary conditions, comparable vacuum states, similar energy distributions, and matching space-time structures, then their boundaries might blend without significant disruption. This is like discovering that your neighbor's house was built from the same blueprint as yours. The moment your properties touch, everything lines up neatly. No walls shift, no foundations tremble. You just share a fence for a moment, exchange a mildly confused smile, and go about your day. Inside such a universe, the effects of the encounter would be nearly undetectable. The early matter distribution would proceed as usual. The background light would retain its smoothness. Gravitational behavior would not pick up any unusual quirks. Even the largest scales, the arrangement of galaxies and the flow of cosmic expansion, would unfold just as they would have without the encounter. The universe keeps its internal harmony because the disturbance at the boundary was too gentle to leave fingerprints. One might wonder how two universes could touch without causing waves, distortions, or dramatic imprints. The answer lies in balance. When two bubbles share similar energy densities along their boundary, the transition between them can be smooth. There is no sudden pressure differential to create shock fronts, no competing vacuum states to force transitions, no turbulent gradients to push inward. Instead, the boundaries meld like two soap films meeting at just the right angle, forming a momentary seam and then drifting apart without ever collapsing each other. This seam, fleeting as it is, becomes a tiny chapter in the shared history of both universes, a moment of cosmological friendship, or at least cosmological politeness. Imagine these universes as colossal beings that accidentally bump elbows, offer a stiff nod, and then proceed in opposite directions. They do not bond, they do not fight, They simply acknowledge the encounter and carry on expanding through the inflationary backdrop like two introverts grateful the interaction was brief. One of the loveliest outcomes of a gentle merger is the possibility that the two universes might share a short-lived interface region that blends their properties seamlessly. This region acts like a thin transitional layer where the characteristics of each universe meet halfway. It does not alter the rest of either universe. It exists only at the boundary, and only for as long as the two remain in contact. Once they drift apart, which inflation nearly guarantees, the transitional layer stretches until it dissipates, leaving each universe unchanged. It is a handshake that leaves no impression, just the faint memory of contact that fades as the universes continue to grow. The optimistic beauty of this scenario is that it paints the multiverse not as a battleground of clashing realities, but as a vast open expanse where most entities coexist without interference. Collisions, when they do happen, do not always result in chaos. Sometimes they are peaceful, harmonious, and downright uneventful. The cosmos, enormous and enigmatic as it is, can also be astonishingly calm, like a sea where waves occasionally overlap without producing storms. And there is something delightfully humorous in imagining universes acting this way. Spacetime, for all its dramatic potential, does not always insist on high theatrics. Sometimes it behaves like a polite stranger at a bus stop, stepping aside to let someone pass and then pretending not to be embarrassed by the brief moment of eye contact. A gentle merger is simply the cosmic version of that small social dance. Two universes cross paths, adjust their boundaries for a moment, and then continue on as though the encounter was just one of those things that happen sometimes in an infinitely large playground. What makes this optimistic scenario even more comforting is that it illustrates how robust the universe truly is. Even when faced with something as bizarre as another universe brushing past, it does not crumble or panic. It stays steady, maintaining its internal structure with unwavering confidence. The encounter becomes a non-event, an interlude so faint the universe barely remembers it. In this chapter, the story centers on peace, on the possibility that reality can engage with other realities gently, gracefully, and without chaos. It is the tale of a cosmos capable of politeness, where universes give each other just enough room to grow, even when their boundaries collide. And in that soft, awkward handshake between two cosmic giants, there is a quiet reassurance. Not every encounter is catastrophic. Some are simply moments of cosmic courtesy before each universe continues on its timeless journey. If universe collisions can nudge, remix, or barely disturb cosmic structure, then there is an even stranger possibility lurking in the more speculative corners of theoretical physics. The idea that such encounters might lead to entirely new physical laws, not just new structures, not just new patterns, but actual rewrites to the deep code of reality. Imagine the cosmos deciding to update its software after brushing against another universe, pressing the metaphorical install patch button and quietly hoping it fixed more bugs than it introduced. Except instead of crashing your laptop, This update would influence everything from the behavior of particles to the shape of space itself. To explore this idea, we first need to understand that physical laws are not commandments etched into cosmic stone. They arise from the configuration of the universe's underlying fields, vast, invisible layers of structure that determine how everything behaves. These fields settle into stable arrangements, much like a computer configures its operating parameters on startup. Change those configurations even slightly, and the entire universe shifts into a new mode. It is the difference between one environment where electrons behave one way and another where they behave differently. In essence, physical laws are the universe's programming language, and collisions might create opportunities for that language to shift. One way a collision could trigger new laws involves the reorganization of vacuum fields that sit at the core of spacetime. If the boundary between two universes introduces an influx of foreign vacuum structure, a slightly different pattern of energy stability, the encounter could encourage the receiving universe to settle into a modified state. Think of this like two pieces of software briefly interacting. The collision acts as a handshake protocol, but the protocol is messy. And during the exchange, one universe accidentally adopts a few lines of foreign code. Suddenly, its operating system boots differently, unaware that the change originated from that brief cosmic contact. This update would not occur everywhere at once. It might begin near the collision interface, where boundary conditions are already disrupted, and then spread inward. Over time, the universe could drift into a new equilibrium, adopting laws that feel perfectly natural internally, even if they are quite different from what existed before. The beings who evolve in such a universe, assuming the new laws still support complexity, would never know the difference. To them, gravity's strength, particle masses, or the behavior of light would be entirely normal, because their world would have grown up under these revised rules. But the speculative fun does not stop there. In some models, collisions could generate hybrid regions, patches of the universe where physical laws differ slightly from surrounding regions. These are not dramatic physics zones marked by glowing barriers or swirling vortexes. They would be subtle, smooth transitions in the behavior of fields. Perhaps particles interact just a little more strongly on one side of the sky than the other. Perhaps certain reactions are slightly more efficient in one region due to small differences in constants. These pockets would eventually blend into the rest of the universe as expansion smooths everything out, but if they lasted long enough, they could influence how matter structures form in fascinating ways. Another possibility is that the collision acts like a catalyst for symmetry breaking. In physics, symmetries determine the behaviors and interactions of particles. When symmetries break, usually during cooling in the early universe, different forces and particles emerge, as if stepping out from behind a curtain. A universe collision could disrupt or accelerate this process. It might encourage one symmetry to break earlier than it otherwise would, or cause a different one to break entirely. This is like discovering that the cosmos has unlocked a new set of features after a software patch, only to realize the patch notes were never released. These speculative outcomes lead to tantalizing questions. What if a collision introduced a new force, one that did not exist before? It might be incredibly weak or incredibly subtle, affecting only rare interactions or exotic particles. Its presence might not be immediately obvious, but its influence could accumulate over billions of years. It might shape cosmic evolution ever so slightly, leaving behind traces detectable only to the cleverest observers. Or what if the collision altered the dimensional structure of the universe, making some dimensions slightly more compact or slightly more expanded? The difference would be imperceptible for everyday life, yet immense in the context of fundamental physics. Of course, not all speculative possibilities are dramatic. Some might involve only tiny tweaks, small optimizations in the universe's code. Perhaps a collision helps stabilize certain fields or smooth out certain irregularities. Maybe it eliminates an instability that otherwise would have emerged billions of years later. In this sense, the universe could genuinely benefit from the unexpected update, emerging cleaner and more refined, like a machine that runs slightly more efficiently because some cosmic bug was quietly patched. And then there is the humorous side of imagining the universe updating itself. One can picture reality pausing, squinting at the unfamiliar data streaming in from the collision, and muttering, "Well, this might as well be an improvement." Then it installs the patch, restarts, and carries on expanding, blissfully unaware that its new behavior might baffle any beings trying to reverse engineer the laws of nature. And if the update introduced its own glitches, well, the universe would simply continue operating anyway. After all, cosmic software does not come with a customer support line. This chapter delves into the most creative corners of cosmic speculation, universes influencing each other not through destruction or distortion, but through gentle, profound reconfiguration. These encounters might rewrite the rules subtly or significantly, crafting entirely new versions of reality. Whether these changes create more stable universes, more chaotic ones, or simply different ones is a question that remains open. But the idea itself highlights the astonishing flexibility of cosmic systems. In essence, a universe collision might not just change the universe, it might rewrite the manual. It might update the code. It might refine or reinvent the cosmos in ways invisible to its inhabitants, yet monumental in the grand cosmic narrative. An eternal software patch installed by the unexpected brush of another reality. If a civilization ever had the improbable privilege, or perhaps the alarming misfortune, of living in a universe drifting toward collision with another, it would face a situation so enormous, so fundamentally beyond instinct or preparation, that even the most advanced minds would feel like bewildered spectators in a show they did not realize they had tickets to. And the most ironic part? The cosmos would give absolutely no instructions, no pop-up alerts, no polite notifications, no comforting message saying, "Your universe is about to encounter unexpected space-time activity. Please save your work." Cosmic warnings rarely come with user manuals, which is admittedly inconsiderate for something so grand. The first signs of an impending collision would not be dramatic. There would be no expanding wall of light, no looming sphere glowing ominously in the sky, no celestial countdown. Instead, the earliest clues would be quiet, subtle, and utterly baffling. A civilization capable of studying the cosmos with exquisite precision would begin noticing anomalies that simply do not fit any internal explanation. Strange directional patterns in cosmic signals, faint distortions in the way light curves across the sky, tiny, inexplicable drifts in gravitational behavior. Nothing catastrophic, just a collection of oddities piling up like cosmic sticky notes, hinting that something unusual lies beyond the usual horizon. At first, these anomalies might seem like calibration errors. Scientists would check their instruments, recheck them, replace them, invent new ones, and still the peculiarities would persist. Perhaps distant regions of the sky would show slight deviations from expected background patterns, like a section of cosmic wallpaper that does not quite match the rest. Researchers might find a directional dependence in certain measurements, suggesting that the universe itself has a quiet preference for one direction, a preference that cannot be explained by internal physics. These hints would be the cosmological equivalent of hearing a faint tapping in your house and realizing it is coming from a wall that should not have anything behind it. As the impending collision draws closer, though closer in cosmic terms could still mean millions of years away, the signatures would grow stronger. Gravitational behavior across vast stretches of space might begin to show gentle shifts. Galaxies could appear to stretch or tilt slightly in a particular direction, not because of anything inside the universe, but because another universe's boundary is approaching, tugging on space-time itself in a manner subtle but unavoidable. Civilization's most brilliant scientists would stare at their equations, whispering phrases like, "This should not be possible," which is how many great scientific revolutions begin. Advanced observatories might detect odd ripples passing through space-time, not the sharp waves from merging stars, but deep, slow undulations that seem to swell across unimaginable distances. These waves would not point to any known source. They would feel as though they originate beyond the observable universe, which would force theorists to confront the unsettling possibility that something enormous exists just outside the region their telescopes can see. Imagine the collective expression of a civilization discovering that space-time is humming a tune they did not realize had lyrics. Eventually, patterns in cosmic background radiation would shift noticeably. The temperature distribution might gain a directional skew, like a faint warm glow in one part of the sky and a cool dip in another, not caused by motion, not by internal structures, but by the gentle approach of another universe's boundary. For a civilization well-versed in theoretical physics, this would be the moment where speculation strengthens into conclusion. Their universe is heading toward a rendezvous with something vast, silent, and utterly outside its own framework. How such a civilization reacts would depend on its temperament. Stoics among them might shrug and say that universes drift where they drift, and very few things can override the momentum of space-time. Alarmists would declare cosmic doom. Philosophers would hold emergency symposiums on the nature of existence, debating whether a collision signifies an ending, a transformation, or simply a new chapter in the universe's biography. and historians would point out somewhat smugly that civilizations have always discovered they understood less than they thought. But what would everyday experience look like? Surprisingly calm. The approach of another universe would not make stars flicker or planets shake. It would not make skies glow or oceans rise. Locally, life would proceed exactly as it had for eons. People would go to work, children would learn math, artists would paint, and the cosmos would slowly drift toward its meeting with no more urgency than a leaf drifting toward the edge of a pond. If you were not one of the scientists studying profound cosmic anomalies, you would never notice a thing. The looming encounter would be as invisible to daily experience as the expansion of the universe is to us now, a grand phenomenon woven so deeply into the fabric of existence that no human sense can detect it. In the final stages before contact, still potentially thousands or millions of years away, the signs would intensify but remain quiet. The sky would not crack. Time would not hiccup. Instead, physics itself would begin whispering louder. The largest scale structures might warp ever so slightly. Extreme precision clocks might tick at subtly mismatched rates when facing different directions. Laser interferometers might detect strange, sluggish waves passing through reality. Only the most sensitive instruments, built by the most persistent scientists, would notice these hints. A cosmic knocking on the door that grows firmer, yet never loud. And through all this, the civilization would face a profound truth. There is no cosmic guidebook for universe collisions, no warnings, no safe practice protocols, no instructions on how to reinforce space-time or shield matter. The cosmos does not distribute pamphlets before major events. It simply unfolds according to whatever rules happen to govern it at that moment. A civilization can prepare intellectually, philosophically, scientifically, but it cannot brace physically against something so enormous. In the end, the experience of an approaching universe collision is not defined by chaos. It is defined by wonder, by the realization that existence is part of a larger expanse than anyone imagined, by the humbling discovery that universes themselves can interact, drift, and evolve. The civilization witnessing such an approach would stand on the edge of cosmic understanding, gazing into a future shaped not by fear, but by awe. This chapter is the tale of that awe. A civilization reading the signs of an impending encounter, recognizing its place in an interconnected multiverse, and confronting the extraordinary truth that even universes can meet, and no one sends instructions when they do. When we reach the end of an idea as vast as universes brushing against one another, reshaping space-time, stirring gravitational tides, or quietly imprinting clues across the sky, we inevitably find ourselves returning to the place where every cosmic question begins. Wonder. Not the kind that flickers briefly when we see a meteor streak overhead, but the deep-rooted, quiet awe that hums in the background of human thought. The feeling that somewhere out there, beyond every horizon, the universe still holds 1,000 secrets, waiting patiently for someone bold enough to ask. It is remarkable when you think about it, that creatures made from stardust, living on a small blue planet orbiting an ordinary star, have the audacity to ask questions about the fate of entire universes. We are built from atoms that only recently learned how to arrange themselves into observers, yet those observers routinely cast their minds outward to scales so enormous they defy intuitive meaning. A person can stand under a night sky, gaze upward, and within moments begin contemplating the birth of existence, the death of stars, the expansion of spacetime, and the possibility that our reality is only one bubble among many. If the cosmos ever feels quiet, it is not because it lacks stories, but because it is waiting for us to imagine them. The idea of universes colliding is one such story, strange, enormous, and profoundly humbling. It invites us to picture our own cosmic home, not as a lonely island, but as one current in a vast ocean of realities, each drifting, shifting, and evolving through forces beyond anything we can sense directly. Even if collisions are gentle, chaotic, improbable, or theoretical, the concept itself pulls us into a deeper relationship with the unknown. It suggests that existence has layers, that reality has rooms we have not yet explored, and that perhaps the largest truths are the ones that require the boldest imagination. And imagination is something humans are particularly skilled at. We do not simply accept that the universe exists. We turn it over in our minds, asking what lies beyond the horizon, under the surface, behind the boundary. We examine ancient light to decode stories billions of years old. We build instruments that can measure ripples in space-time smaller than an atom. We propose theories about events no living creature could ever witness firsthand. This capacity to wonder, to imagine, to ask, what if, is the hallmark of our species, more defining than any technology or invention. Before we built telescopes, we built questions. In contemplating universe collisions, we are really contemplating ourselves, how we think, how we search, how we dream. We are acknowledging that curiosity is not merely an intellectual habit, but a fundamental part of being human. The universe does not send us invitations to explore. It does not announce its mysteries, and yet we search anyway, piecing together clues from light, gravity, and mathematics like detectives of the infinite. Every discovery raises new questions, and every question leads to new realizations about our place in the cosmos. This is why cosmic speculation is not a frivolous exercise. It is a form of connection, a way of participating in the universe rather than simply inhabiting it. When we imagine universes brushing against each other, we are expanding the boundaries of what reality might include. We are practicing the art of thinking beyond the known, pushing into territories where certainty fades and curiosity becomes the guiding force. In these imaginative spaces, we recognize that our minds are capable of reaching far beyond our physical scale. A single thought can travel further than any spacecraft ever built. As we reflect on the idea of universe collisions, we realize that our fascination with the cosmos is not driven by fear, but by an innate sense of wonder. Whether universes collide gently, violently or not at all, the act of pondering them enriches us. It stretches our understanding, sharpens our questions, and reminds us that reality is not limited to what we can see. Even the possibility of other universes drifting near ours, touching ours, or influencing ours opens the door to a deeper appreciation of how magnificent existence truly is. And perhaps the most beautiful part of all this wondering is that it highlights how much we still have to learn. We do not know how the multiverse might work. We do not know what lies beyond our cosmic horizon. We do not know whether universes collide, merge, or interact. But we do know that asking these questions brings us closer to understanding the universe we inhabit. Curiosity is the force that propels us forward, a kind of intellectual expansion that mirrors the physical expansion of space-time. It drives us to look up instead of down, outward instead of inward, forward instead of backward. In this sense, the story of universe collisions is not just a tale about vast celestial bodies drifting through an unimaginable landscape. It is a celebration of the human drive to explore the unknown. It is a reminder that wonder is the source code of discovery, and it is an invitation, not from the cosmos, but from ourselves, to keep imagining, keep questioning, keep reaching. So even if universes do collide, brushing past each other in ways we can barely detect or fully comprehend, there is something larger and more enduring at play. Something that expands faster than space-time, stretches further than any boundary, and survives every cosmic shift. Our curiosity.